Do you want? So, do you need a slide thing? No.
And now we will be covering the inner product. Specifically, we'll go over the axioms that make the inner product something you can do. We will go over how to calculate it if it's real, such as a Euclidean function or Euclidean number, or yeah, Euclidean real number. A continuous function. We also go over Hermitian inner products, which are basically just complex, inner products. And then from that, we can prove the Cauchy-Schwarz inequality. And using the Cauchy-Schwarz, we can find defining angles or angles in like a vector and magnitude and all the fancy stuff. And from there, we can also find the triangular inequality. So for the first one, for Euclidean real numbers, the inner product basically states that if there exists a vector space V that is real, there exists one real number denoted by u comma v to each pair of vectors with u and v within vector space V. In order for this to happen, you have to make sure this vector space follows three axioms. One, it is linear, so it's closed under scalar addition or multiplication. Two, it's symmetric, so the inner product of u comma v should be equal to the inner product of v comma u. And three, the inner product of u of itself is greater than 0, if u, of course, is not 0. And this is all assuming that u and v are vectors. Another way we can denote the inner product is basically the transpose of u vector times the vector v. And the next part of the inner products we'll be covering is real continuous function. So it's pretty much the same, except instead of numbers this time, you are using functions of x, t, doesn't matter what the variable is, but as long as it's something you can integrate. So on an interval like from a to b, if v is a vector space of a real continuous function and the inner products of f of x and g of x, then the integral should be from a to b of f of x times g of x, and you're trying to find for x. Again, you have to have the three same axioms you did for real Euclidean inner products. So it has to be closed under scalar addition and multiplication. It has to be symmetric, and the inner product of u of itself is greater than 0 if u is not 0. And now we go to Hermitian inner products, which are basically complex inner products. So it states that if there exists a vector space V that is complex, there exists one complex number denoted by the inner product of u comma v to each pair of vectors of u v within vector space V. In order for this to happen, three axioms need to be satisfied for this inner product to be complex. One, it has to be linear, so closed under scalar addition and multiplication. And this time, instead of it being symmetric, it has to be non-symmetric. So the inner product of u comma v should be equal to the inner product of v comma u conjugate of that. So u comma v, the inner products of that, should be equal to the conjugate of v comma u, basically. And the positive definite property again, which is basically if u is not 0, then the inner product of itself is greater than 0, right? For finding inner product, if it's just numbers, it's basically u conjugate times v, or u conjugate transpose. That's what this line here is basically. Okay, and then there's also a way to compute it with integrals. If you have a function u of t, v of t, where t can be any variable pretty much, it's closed in a vector space C is equal to AB, and it goes from, so the integral is basically, instead of just being ut vt in this case here, it's going to be u conjugate of t vt dt in this integral. So it's a little bit different to real, because you have to take the conjugate of u of t. And then u of t in this case would be something where u of t is f of t equal plus I g of t. In real examples, g of t would be 0, and you just have f of t. So it's just f of t v t, right? But yeah. And here's a little example here. So if u of t is equal to t plus I, and v of t is equal to t, and t spans from 0 to 1, then the inner product of t plus I and t should be equal to pretty much 1/3 minus 1/2 I, right? And now that we know pretty much the inner products of real and complex functions and numbers, we can pretty much derive the Cauchy-Schwarz inequality, which basically states that the inner product of u comma v squared is less than or equal to the magnitude of u squared times the magnitude of v squared. And there's two ways to prove it. I like the quadratic form. So basically it says that if there is, for any t within a real number space, such that tu plus v, or the inner product of tu plus v by itself is, is equal to t squared, the magnitude of u squared, plus 2t times the inner product of uv plus the magnitude of v squared is greater than 0, then the quadratic has no real roots if it doesn't satisfy b squared is greater than or equal to 4ac. So in this case, ac is 1, or a is 1, and c is 1, so it's just 4. B squared is 2t. And remember to put the variables in there too. So basically, if you plug everything in, you should get this inequality right here. And then that simplifies to the Cauchy-Schwarz equation, inequality. And here is what I'm talking. This is what I mean when I'm saying defining angles. So basically, this is, you derive this from the Cauchy-Schwarz inequality, and so basically you take the square root of, or you divide the magnitude from the right side of the Cauchy-Schwarz inequality. So you get the inner product of uv squared over the magnitude of u squared, the magnitude of v squared is less than or equal to 1. And then if you take the square root of both sides, you just get the magnitude of u comma v, or the inner product of u comma v is over the magnitude of u and the magnitude of v should be from 1 to -1 because -1 squared is 1, right? So it satisfies this inequality. This is pretty similar to cosine from 0 to pi because cosine alternates if it's between 0 and pi, right? So you can say that cosine of theta is equal to inner product of u comma v over the magnitude of u times the magnitude of v. And then to find the angle, you just take the inverse cosine of both sides. And that's what we're trying to do here. So we are trying to, here's an example using the inner products. Given that f of t is equal to t squared plus 1 and g of t is equal to t squared minus 1, and t is from 0 to 2, of course f of t and g of t in this case would be the inner product. So we first find that to find the angle, right? And then we should get 22 over 5, right? But the magnitude of f of t and the magnitude of g of t are a little bit different from that. So to find f of t, what we do is basically we take f of t and we find the inner product of it with itself. So in this case, it's 206 over 15. And then after we find that, so that's the magnitude of f of t squared, right? It's equal to 206 over 5. So then we take the square root of both sides, and then we should get our f of t. So then we can just plug that back in the original equation. For g of t, we do the same process. And in this case, we get the magnitude of g of t is equal to 146 over 15, all in the square root. And we plug it back into the original angle formula. And so we take the inner, so we basically plug in what we just solved. Then we should get this answer right here once you take the arc cosine, or the inverse cosine. Another thing we can also prove with inner product is the triangular inequality. So the way they do it in the handout and the way we do it here is that we just take the magnitude of u, of quantity u plus v squared, and then we use the inner product definition to expand it out, right? So we plug this in here. After, of course, squaring the magnitude of quantity u plus v is less than or greater to magnitude of u plus the magnitude of v. So we get this equation for the left side after we plug in, and then for the right side we get this equation. And we can simplify this down to magnitude u plus v, magnitude quantity u plus v squared is less than or equal to the magnitude of u, the magnitude of v, plus the magnitude, sorry, the magnitude of u plus the magnitude of v squared, and then you could just basically simplify that down to the triangular inequality. And here's an example of the Fourier basis. So basically what you have to do is you have to take the basis times itself and the basis times the other bases in the sort of the basis, right? So the basis times itself, you should get pi, or for cosine of nx, so, and then you should get pi for cosine of mx too. So sine of nx times itself should get pi, and cosine of nx times itself should be pi if it's taken using inner products. Same thing with 1, you should get something a little bit different, 2 pi in this case. In this case, it's from pi, inverse from pi to negative pi, so that's what you should get. The bases with each other are similar. You basically do each basis with another base in the Fourier expansion, or not the Fourier expansion, the Fourier set you're given, and then you just basically find the integral. They should all be 0 because the basis is all orthogonal of each other, since the inner product is 0, right? It's because inner product is basically dot product, and the dot product is zeros, right? Vectors are orthogonal with the one you took the dot product with. But if it isn't 0, again, the basis is orthogonal. All right. However, we take the inner product of a basis with itself, and if it's not 0, that means it's not orthonormal. So to get it to orthonormalize, we basically just divide by the magnitude of both vectors. And now we go to linear transformations.